Today we are going to see about the fundamentals of symmetrical components. So what is meant by symmetrical components and unsymmetrical components? So symmetrical components, what is the basic thing is that, so it is one of the most powerful tools for dealing with the unbalanced polyphase circuits. So by using the symmetrical components. So what we are doing is the unbalanced polyphase circuit. If you just practically calculate this unbalanced polyphase circuit, solving the problem is very complex. Solving the problem is very complex. So what we are doing is we are considering that with the symmetrical components that all the phase shift between the phases, say for example A, B, and C phase, having the equal phase shift, like 120-degree phase shift, like that, then we are going to solve the problem. So what happens if you solve with a squared like that, a cube like that, means if you solve like that, you're solving the problem will be very easy, because no much complex calculation will be there. Otherwise, say for example, if the displacement is there, say for example, the angle displacement is there. So then you need some more time to calculate that angle displacement and all. Say for example, simple system, okay, in complex system where more buzzes are there, that analysis of the short circuit, say for example, analysis of the short circuit is very complex there. If you consider that will be a symmetrical component, then analysis of the short circuit also will be very easy. The unbalanced system of n related phases can be solved into n system of balanced phases. So unbalanced system also may be converted to the balanced phases, that is called the symmetrical components. Three-phase systems are normally balanced or unbalanced under the fault condition. So three-phase systems, if you take the three-phase system, generally it may be balanced or unbalanced under the fault condition. Mostly it might be unbalanced only. Sometimes it may be balanced. So what is meant by balanced system? Balanced system, the load impedance are the same in all the three phases. In the balanced system, all the load impedance are the same. And the voltage and current are characterized by the complete three-phase symmetry. Complete three-phase symmetry, as we said, three-phase symmetry means all at the angle of 120-degree apart. So for analysis, we use per phase basis. So what we are doing is we are considering that to per phase basis. Next, the algebraic sum of the balanced three-phase current is zero all the times. Algebraic sum of balance, say for example, IA plus IB plus IC is equal to IN. That is the phase current in the I phase and the phase current in the B phase and the phase current of the C phase. That is equal to the neutral current. That is equal to the zero. No current will flow between the generator or transformer, neutrals and ground. That is, there will be a no current flowing between the transformers or transformer neutrals and to the ground. So that is called your balanced system. What is this unbalanced system in the sense? In the unsymmetrical faulted or loaded system, neither the phase current nor the phase voltage possess this three-phase symmetry. Three-phase symmetry, this already we have seen. The algebraic sum of the phase current is equal to the neutral current flowing in the system. The algebraic sum of the phase current. Say, for example, IA plus IB plus IC is equal to IN. There will be some currents. Algebraic sum of the phase current is equal to the neutral current. That neutral current may be some currents, because in the unsymmetrical currents, this currents will be, the phase current will be changing. So at the resultant, neutral current will be some current. There will be some current or some voltage. The potential of the generator neutral Vn will be equal to the ground potential minus the drop over the Z. That is the impedance at the neutral. The potential of the generator neutral will be equal to the ground potential, that minus the drop over the Z in the unbalanced phase. Whereas this becomes zero in the balanced phase. That is the difference. The unbalanced generator equivalent circuit is so. So this is the unbalanced generator equivalent. Say for example, this is the A phase, B phase, and C phase, having the impedance of ZS in all the phases. So here it is the Zn is the neutral impedance that is grounded here. So what happens in the unbalanced system? Say for example, Vn is equal to Vn, that is neutral voltage, is equal to Va plus In into Zn. Va plus In into Z. So what is this? Va means voltage at that particular phase. Voltage at that say for example it is a phase. So say for example in this phase we have considered the current is flowing in this direction. Generally, the current will flow in this direction only, that is to the ground. But due to some unbalanced condition, what we have considered is, we have considered the current is flowing in this direction. So here the voltage at the particular some particular phase is 0, and the current is in the opposite direction. So minus In into Zn. Like where Vn is the potential of the generator neutral, and Zn is the neutral impedance. Symmetrical components are applied to the unbalanced fault, that is line to ground, line to line, and double line to ground, are analyzed using simple per phase basis. Two functions are developed for the symmetrical component transformations. These are the transformation from the phase quantities into symmetrical components, and the transformation from the symmetrical components to the phase quantities. Say the symmetrical components allow unbalanced phase quantities such as current and voltage to be replaced by the three separate balanced symmetrical components. So what happens is, symmetrical components allow the balanced phase quantities such as current and voltage to be replaced by the three separate balanced symmetrical components. Next, what are the effects of unbalanced loads in the star system? In unbalanced four-wire star load, that is neutral also there, the currents are different. So if it is unbalanced, but in the balanced condition, all the current in the star connection are same. But still, each phase receive equal voltage. Neutral wires takes the unbalanced current and helps maintain the equal voltage to the each load phase. So what happens is, in the unbalanced four-wire star load, even though the current are different, but still the phase receive equal voltage. So each phase receive the equal voltage, but the neutral wire takes that unbalanced current. Neutral wire is there now, that is four-wire star connected. In that center, neutral wire will be there. So that neutral wire carries the unbalanced current that helps the maintain the equal voltage to the load phase. Without the neutral, each phase will receive the different voltage. So if the neutral is not there, so every phase will receive the different voltage. So what is the phase sequence? In the three-phase system, the phase sequence is defined as in order which they pass to the positive maximum. Consider the unbalanced current IA, IB, and IC. Say for example, this is the unbalanced current IA, IB, and IC. So which having the phase shift of 120 apart. So here what happens is, there is some loss. There is some loss resultant component. Resultant component, we have the resistant component and as well as the reactive component. There is some drop. Current drop will be there. So that current drop carries your resistant component and as well as the reactance component. So this is the resultant one. For IA, this is the resultant one. Similarly, for all the phases. Say for example, this is the IC, this is the resistance component, this is the reactance component, and this is the resultant component. Similarly for IB, this is the resistive component, this is the reactive component, and this is the resultant component. Like that, this is the unbalanced current IB and IA, IB and IC. these currents are resolved into three-phase symmetrical components. They are positive, negative, and zero sequence. Now we'll see about what is positive sequence components. What is positive sequence component is? It consists of three components of equal magnitude. Three components of equal magnitude displaced by 120 degree in phase and having the phase sequence of A, B, C as shown in the figure. So what is positive sequence component is? Say for example, if you take this as IA, or this is the A component, that is the current carries is IA, and this is in this anti-clockwise direction. So this is IA, IB, and IC, which is having the phase shift of 120 degree apart. So each one phase having the 120 degree phase shift. That is the phase shift from IA and IC is 120 degree, and IC and IB is 120 degree. Similarly, IB and IA is also 120 degree. Let IA plus be the reference phasor. The positive sequence phasors A, B, C can be written in terms of IA plus, that is a positive sequence current component. How to write all these three phase currents, that is IA plus, IB plus, IC plus, in terms of IA component is IA plus is equal to IA plus at the angle of 0 degree that you know. Next, IB plus is equal to IA plus at the angle of 240 degree. That is nothing but A squared into IA plus. Next, IC plus is equal to IA plus at the angle of 120 degree. That is equal to A into IA plus, where IA plus, IB plus, and IC plus are the positive sequence components of IA, IB, and IC. These are the positive sequence currents, that is, are otherwise positive sequence components. That is components of IA and IB and IC. That is IA plus, IB plus, and IC plus. Next comes the negative sequence components. Negative sequence components, it consists of three components of equal magnitude displaced by 120 degree in phase and having the phase sequence A, C, B as shown in the figure. Say for example, in the negative sequence components, say this is the IA negative, this is the IC negative, this is the IB negative. So here, if you compare with the positive sequence component, it is IA, IB, and IC. But in the negative sequence components, it is IA minus, IC minus, and IB minus, and which is having the phase shift of 120 degree apart. That is between IA negative and IB negative 120 degree, and between IB negative and IC negative, it is again 120 degree. Between IC negative and IA negative is 120 degree. But you need to follow the phase sequence as A, C, and B. That is in anti-clockwise direction. A, C, and B. Let IA negative be the reference phasor. Next, negative sequence phasors A, B, C can be rewritten in terms of IA negative as, that is, three phases are written as IA negative is equal to IA negative at the angle of 0 degree. That is nothing but IA negative. That is 0 degree have no values. And here IB negative is equal to IA negative at the angle of 120 degree. That is nothing but A into IA negative. And next, IC negative is equal to IA negative at the angle of 240 degree. That is nothing but A squared IA negative or IA minus. Here, where IA minus, IB minus, and IC minus are the negative sequence components of IA, IB, and IC. So what we are doing is here, we are writing this all three phase currents, that is IA minus, IB minus, IC minus in terms of IA minus, and with the corresponding phase sequence. What is this zero sequence component? Zero sequence component, it consists of three phases equal in magnitude with a zero phase displacement from each other as shown in the figure. That is zero phase displacement from each other as shown in the figure. So this is the IA, that is IA naught, IB naught, and IC naught. So you can write, you can draw like this, or otherwise in one single shift itself, in one single arrow mark, that is current itself, you can write IA naught, IB naught, IC naught. Actually, they for a differentiation they kept like this, but you can also write in all IA naught, IB naught, and IC, because this is having zero displacement and having equal magnitude for all the three phases. So zero sequence phases A, B, C can be rewritten as IA naught is equal to IB naught, that is equal to IC naught, where IA naught, comma, IB naught, and IC naught are the zero sequence components of IA, comma, IB, and IC. So these are the zero sequence components.